So what we're going to be doing here in this video is we're going to do another limiting and excess reactant problem. Now if you watch the first video I did on this, I calculated or I did a method of finding the limiting and excess reactants where we took masses of both of our reactants and converted that to the mass of the product, and whichever one produced the least amount of product, that was our limiting reactant. There's more than one way to do this, so in this video I'm going to do a little bit different way of explaining how we can solve for our limiting and our excess reactant. And the reason that we need this first is it's because it's our limiting reactant that controls how much product we make. So you can see here that we have a balanced equation. This is the combustion of propane, and 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of CO2 and 4 moles of water. Alright, so let's get going down here. We have, as it says in the part A here, to identify the limiting and excess reactants if we have 80 grams of propane combusting with 150 grams of oxygen. Now if you've not done this much, you may be tempted to want to pick this 80 grams of propane because it's less than 150 grams of oxygen. But let's go through this process and see really which one's limiting here. So we have 80 grams of propane. And what we're going to do this time around is we're just going to convert this to moles first. So 80 grams of propane divided by its molar mass, so this is going to be grams of propane, C3H8, to moles of propane, C3H8. We need a little bit bigger line there. Okay, a mole of propane is, let's go over here to our periodic table. Oh, that's all we needed to do. We can see carbon is 12.01, and we have 3 of them, so times 3. And we're going to add that to 8 hydrogens. 8 times 1.01. If we drag our periodic table over here, we can see that hydrogen, rounded to the hundredths place, is 1.01. So 3 times 12.01 is 36.03, and 8 times this number here, 1.01, is 8.08. And so the molar mass of our propane is 44.11. So, change color here. 44.11 grams of propane per 1 mole. So, let's see. So, let's pull this over here. Let's go ahead and write that down. Go ahead and calculate that. Let's grab our calculator here and put in 80 divided by 44.11. And we get 1.81 rounded to 3 significant figures. So 1.81 moles of propane. And then we're going to do the same thing for our oxygen down here. We have 150 grams of oxygen, that's O2, and we want to go to moles of oxygen to start with. So we're going to need a molar mass of oxygen. Now remember, this isn't elemental oxygen, this is an oxygen molecule. So we're going to need the molar mass of 2 oxygens here from the periodic table. So that is 2 times 16, which is easy enough to do in our heads, right? We got 2 times 16 is 32 per 1 mole. So we grab our calculator and we have 150 divided by 32. And that gives us 4.68, and rounded to 4 significant figures in this case. We can go all the way out here to this 7, but for what we're doing, keeping just 3 of the digits here is fine. So 4.68 moles of oxygen. Alright, so how does this help us? This may or may not necessarily determine the limiting, because again, if you just try to pick the smaller one, you may or may not be right. So what we need to do is we need to decide how much oxygen are we going to need to use up all of this propane. So what we can do here is just a mole conversion. We can say, alright, our balanced equation says that for every 1 mole of propane used, 1 mole of propane used, we will need to use 5 moles of oxygen. So here we are. Bring up our calculator. We have 1.81. Let's move it over here. 1.81 times 5. And we get 9.05. What this tells us is that for all of this propane to be used, we're going to need 9.05 moles of oxygen. Now, you've already calculated how many moles of oxygen you actually have. If you look down here, you'll see that you actually have only 4.68 moles of oxygen. But your calculation up here says that you need 9.05. So you don't have enough oxygen. So this has answered your question. Oxygen is your limiting reactant. You do not have enough of it to react all of your propane. But if you kind of want to confirm that, you can do a mole-to-mole conversion from oxygen to propane, and it will show you that you will in fact have an excess of propane. So we have a mole conversion. Our balanced equation tells us that 5 moles of oxygen are used per 1 mole of propane. So 5 moles of oxygen are used per 1 mole of propane. And we can already see that our answer is going to be less than 1, right? And we have well over 1 mole of propane, but we'll go ahead and do it just to be good and thorough here. We have 4.68 divided by 5. And this little calculation tells us that we need 0.94 moles of propane. So 0.94 moles of propane is what we're going to need for this oxygen. And you can see, again, here, we have 1.8. So we have an excess of oxygen. So either one of these would have given you the answer without having to do the other one, but it is good just to be thorough to maybe do both of them just to double check in case you made a mistake here. So our limiting reactant is our oxygen. We don't have enough of it to use up all of our propane. And so it's our oxygen that we're going to use to calculate the masses of our products. So what we're going to do first here is write this down over here just to remind us. We have our limiting reactant is our oxygen, and our excess reactant is our propane, C3H8. Right, we're going to be able to get rid of all of our math down here. Okay, so let's calculate the mass of both products. It says here in B to calculate the mass of both products formed, that's CO2 and water. So we're going to have to do 2 separate problems here. It doesn't really matter which one you choose to calculate first. You'll get the same answers either way. It just depends on which one you'd like to do first. I'm going to choose CO2, but again, it doesn't matter which one you choose to do first. We know our limiting reactant is oxygen. So we have 150 grams of oxygen. And we want to convert that to a mass of, in this case, CO2. So we know from our previous problems there that there are 32 grams of oxygen in 1 mole of oxygen. Our balanced equation tells us that 5 moles of oxygen are used to produce 3 moles of CO2. Okay, remember to cross these off as we go. I've been forgetting that. And finally, we want to make sure we convert from moles of CO2 to mass of CO2. So, moles of CO2 to a mass of CO2, grams CO2. All right, so 1 mole of CO2 is, and we'll go over to our periodic table to calculate our molar mass. We have 1 carbon, and we have 2 oxygens. So 1 carbon is 12.01, and 2 times 16, that's 2 oxygens, that's 32. So our molar mass is 44.01 grams per mole for CO2. So we can go back over here, and we'll plug that into our missing spot here. We have 44.01 grams of CO2 per mole. This is going to give us how much CO2 we've produced. So let's bring our calculator back up, And maybe drop it down here to see our numbers. We have 150 times 3 times 44.01 in the numerator. So 150 times 3 times 44.01. And we're going to divide that by our denominators here. Now our other denominator here is a 1, so we can kind of ignore that. So we're going to divide this by, and we'll open our parentheses, 32 times 5. And we get 123.778125. So we look back here and we see that all of our numbers here have 4 significant figures. So our answer should have 4 significant figures. So this 7 here will round this 7, our 4th significant digit, up to an 8. So we have 123.8 grams of CO2 produced. Now, we're going to have to do it again because this is only one product. That was only CO2, and it asks us to solve the mass of both products. So we're going to do it again, except for this time, instead of going to a mass of CO2, we're going to go to a mass of water. So start over again at 150 grams of oxygen. And we're going to go from grams of oxygen to moles of oxygen. And we're going to look at the balanced chemical equation to sort of bridge this gap here. Our equation tells us that 5 moles of oxygen will react to produce 4 moles of water. So that's what we'll put down here. 5 moles of oxygen will react to produce 4 moles of water. And then finally, we want to go from moles of water to mass. So 1 mole of water is, we'll have to go back over to our periodic table to get this. Oh, some past math there we'll get rid of. So H2O, that is 2 hydrogens. Let's get a better color here. It's 2 hydrogens. So 2.02, rounded to the hundredths place there, 1.01 times 2. And 1 oxygen. It's 16 grams per mole per oxygen. So 18.02 grams per mole is the molar mass for water. Okay, so we'll put that in right here. 18.02 grams of water per 1 mole. And we're able to cross all these off. Oop, I forgot to cross these off up here. And we'll be left just with the unit of the answer that we want, grams of water. So let's grab our calculator again. We have 150 times 4 times 18.02. So 150 times 4 times 18.02. And we're going to divide that by, again, 32 times 5. We can ignore this 1 here. Make sure we put that in parentheses if you're going to do it all at once as well. So 32 times 5. And that gives us 67.57. And we have 4 significant figures here, so we want to round that to 4. So 67.5, and we'll let just this 5 round bump that up to that even number 8. So 67.58. grams of water. All right, so we've solved part B, to calculate the mass of both products. Now, the next part, it says to go ahead and calculate the mass of the excess reactant remaining. So we're going to run out of space. Let's just go up here and kind of write down what we have. We have 123.8 grams of CO2. We have 67.58 grams of water. And the rest of this is asking us to calculate the excess remaining after this is reacted. So we know that oxygens are limiting. We want to know how much propane is left over once we've run out of our oxygen. So it's really, again, not that difficult of a problem. What we're going to do is we're just going to do some math. We're going to use law of conservation of mass here. So we have 80 grams of propane on the reactant side, plus 150 grams of oxygen. So total mass of reactants, let's put this up here so we know what we're doing. This is mass of reactants that we're calculating here. total mass of reactants is 230 grams. Now let's look at our products here. We need to add these up. We have 123.8 grams of CO2, and we have 67.58 grams of water. Now the rules for significant figures when it comes to adding tells us that once we're done adding, we're only going to keep the least specific decimal point that they all have in common. And so here it's the tens place. So we're going to get our calculator out and add it up, but we're going to round it to the tens place. So we have 100, oops, one too many, and 23.8 plus 67.58. Oop, that said 57. I made that mistake. Let's try that again. We have 123.8 plus 67.58. It gives us a total of 191.38. But we're going to round to that tenths place there. So we'll call this 191.4. So we have 191.4 grams of products. That's both CO2 and water. So, law of conservation of mass tells us that if this is how much product we have, whatever the difference between these two numbers right here, this number here, total mass of reactants, and this number here, mass of products, has to equal whatever is the left over, whatever amount of excess reactant propane here is left over. Because of this 191.4, 150 of it is all of our oxygen. Remember, oxygen was our limiting reactant, so it's all used up. So let's grab our calculator out here one more time. We have 230 minus 191.4. And we get 38.6. So we have 38.6 grams of our excess reactant C3H8 remaining. So we'll write that up here as we have a list of answers. 38.6 grams C3H8 remain unreacted. Okay? Now, on to C. Calculate the mass of the limiting you would need to add to use up the rest of the remaining excess reactant. So, again, this question is just asking, how much more oxygen, our limiting reactant, would we have to add so that all of this 38.6 grams of remaining propane would be consumed? And so really this is just a mass to mass stoichiometry conversion. We're going to go from our mass of propane to a mass of oxygen, and that will let us know how much oxygen we're going to need to burn up the rest of this propane. So 38.6 grams of propane. All right. So we need a molar mass, and if we kept all of our numbers, which I unfortunately erased, but I think I can remember here, then we don't have to do all the extra addition here. I think we had, 44.11 grams of propane per 1 mole, I believe. And our balanced equation tells us that 1 mole of propane 1 mole of propane will react with 5 moles of oxygen. So we're going to put that here, 5 moles of oxygen. And so that gets rid of moles of propane, grams of propane. Now we're at oxygen. And we look here and we know that 1 mole of oxygen is 32 grams. Remember, be careful. This is a molecule of oxygen, not elemental oxygen. So we'll use 32 and not 16. So let's grab our calculator here. Oh, let's get this out of the way. So we're going to 38.6 multiplied by 5 multiplied by 32 divided by, and make sure you use parentheses here. Oh, well, actually, we don't need parentheses. We only have one number other than 1 in our denominator, so we can just go ahead and divide by 44.11. Oops, one too many again. and we get 140.0. So we have 3 significant figures here, so we'll just keep this at 3 significant figures, 140. So it would take approximately 140 grams of oxygen to react with the remaining propane. We're almost done. One last problem here. Down here at D, it says, okay, maybe I should emphasize what this is. 140 grams of oxygen needed to react with the 38.6 grams of propane. So if you're taking notes down there, you know what this number is for. So the last thing we're going to do here is this little percent yield problem. Now, if you watched the last video, you'll see kind of how we did this here. Basically, what we're saying with percent yield is, well, we're not able to get all of the water or all of the CO2 out of a reaction, and a percent yield is kind of a nice way to sort of tell us how well we've done. So we just have this sort of scenario they've given us here. We have an experimental yield of 38 grams of water. So a couple scientists have gone to a lab, combusted some propane, and they only get 38 grams of water. And theoretically, how many grams of water could they have gotten? 67.58. We're going to multiply by 100 so we can scale this up to 100. And let's calculate our percent yield. 38 divided by 67.58 gives us 0.5622. And if we multiply by 100, remember, if you want to save yourself a step in the calculator, we're just bumping the decimal over twice for a percentage. That's all multiplying by 100 is going to do for us. So we get 56.2%. 56.2% yield.